Hey everybody, this video is about center of mass, which is just another type of centroid, right? We've been learning area-weighted mean position, so like this, right? Area-weighted mean position, but this can be anything. It can be volume, it can be length, dollars. If it's mass-weighted mean position, then that's center of mass, which we just label it like this, center of mass. It's like special mass-weighted mean position, analogous for y. Okay. And note that if you have a situation where the density of an object is constant throughout, then we say that it's homogeneous. And you can define density, kind of depends on the context. So it can be mass per volume, differentially, right? So mass per volume. So if you define this, notice that you can say that dm is rho dv, and if you replace this, let's just focus on one of these. If you replace this here, right, then you get something that looks more like rho dv. And if the object is homogeneous, then the density is constant, which means you can take it out of the integral. And then in which case the numerator and denominator cancel. And look at this. It's just a volume-weighted mean position. Of course, you can, let's say you have an area, you can define density as mass per area, and then dm becomes rho dA, and then you change these to area, right? And then you have an area-weighted mean position, right? So it just depends. If you have like a bar, then you can define density as mass per length. And then, right, when you compute the center of mass, density factors out, leaving you with rho dl. And then it becomes a length-weighted mean position. Right? So it just depends on the geometry of the object. So here's an example with a bar. So we want the center of mass, and we are given that it is homogeneous, so it's constant density throughout. If we want the mass-weighted mean position, that's center of mass, right? So it looks like, and to me it looks like a composite of 3 bars. So it looks like, I'll say like this is bar 1, I'll just call it 1, and then this bar, and this bar. And for bar 1, the centroid is in the middle, for bar 2, in the middle, for bar 3, in the middle. So if I want the mass-weighted mean position, the centroid for bar 1 times the mass of bar 1, centroid for bar 2 times the mass of bar 2, etc. for bar 3, over the total mass, 100 kilograms. I don't know right now these values, but if we're saying it's homogeneous, that means the density is the same everywhere. So for bar 1, the mass of bar 1 over its length is the same as for bar 2, its mass over its length, same for bar 3. And if you look at this, that means M1 is rho L1, M2 is rho L2, M3 is rho L3. And substitute these here. And then what happens? Density cancels everywhere, and you end up with what ends up being a length-weighted mean position. Because density cancels in numerator and denominator. Right, so let's say if you want to just plug in numbers. So x component of centroid for bar 1 is 0.5, the length of bar 1, plus the x component here is 1 meter, the length of bar 2, and then here to here is, let's see, here to here is half, here to here is 0.25, so that's 0.75. And then the length of bar 3 is 0.5 over the whole thing, right? 1, 2.5. Okay, so then that's the x component of the centroid. And then in the y direction, like I'll just say, right, in the y direction, the centroid for that is 0. For this one is half a meter, and then for this one is 1 meter. Okay, so give some of these center of mass problems a try, and let me know if you have any questions. I'll see you on the next video.